On behalf of the NRAO, I'd like to welcome each of you to this year's Jansky Lecture. This distinguished lecture series was established by our parent organization, the Associated Universities Incorporated, or AUI, to honor Carl Jansky, who in 1932 first detected radio signals from beyond the Earth, in fact from the center of our galaxy, thereby founding the science of radio astronomy, or the observation or the study of the universe by observing radio waves instead of visible light. At this point, it's our pleasure to welcome David Jansky, Carl's son, and Curtis Jansky, Carl's nephew. And today it gives me great pleasure to welcome my old friend and colleague, Tony Readhead, Barbara and Stanley Rowan Jr. Professor of Astronomy at Caltech, as this year's Jansky Lecturer. Tony studied physics and mathematics at the University Witwatersrand in South Africa, and he continued his education in England at the Cavendish Laboratory at Cambridge University, where he conducted doctoral research on active galaxies and interplanetary scintillation under Anthony Hewish, who was the winner of the 1974 Nobel Prize in Physics. Tony was awarded the Royal Society Weir Research Fellowship that he divided his time on between Cambridge and Caltech in the mid-70s. And in fact, in 1974, where Tony and I were fellow postdocs at Owens Valley at Caltech, and at that time, I watched closely over 2 years how he and Peter Wilkinson, now professor at Manchester University, worked daily to develop what's called the technique of hybrid mapping of very long baseline interferometry observations. The significance of this is, of course, that this method enabled radio astronomers to make pictures of radio waves from the center of active galaxies at resolution 100 times better than what the Hubble Space Telescope can achieve today. And I believe Tony would tell us today what he and his colleagues have unraveled about the inner workings of active galactic nuclei, and largely aided by this pioneering work of his from those days. Tony returned to Caltech in 1977, and he was appointed professor of astronomy in 1981. And between 81 and 86, he was a director of the Owens Valley Radio Observatory, the observatory at Caltech. And following his election to the National Academy of Sciences and the American Academy of Arts and Sciences in 1995, Tony led a team that developed, built, and operated this first of its experiments of this type, the Cosmic Background Imager, to measure the microwave background radiation, total intensity, and polarization power spectra at small angular scales. It's from detailed measurements of this sort that CBI and similar experiments that found that we today have gained the understanding that the universe is nearly flat. It is 13.7 billion years old, and 95% of its content is basically unknown. Tony continues his work in this area, collaborating on the QUIET experiment that is attempting to measure the polarization of the CMB radiation, and he's also working on the development of coherent detector arrays for radio astronomy. I was told by Tony that in fact he had to have a debate with himself on which topic to lecture on today. It's microwave background radiation or active galactic nuclei. Well, his choice is today's Jansky lecture entitled The Central Engines that Power Active Galaxies. Tony.
Thank you very much. Thank you. Thank you very much, Fred, for a very kind introduction, and thank all of you for coming today. It's a great pleasure and, of course, a great honor to be here today to give this year's Jansky lecture. and I'm most grateful for the invitation. Thank you. So today I'll be talking about the interplay between technology and science. That's a critical theme of what I'll be saying today. And this interplay is, of course, critically important in astronomy. And I thought I would begin with a quote from A Room of One's Own by Virginia Woolf that reminds us all of the interdependence that's the basis of all our scientific and indeed our artistic enterprises. And I find it particularly interesting to keep in mind that when the example that Virginia Woolf had in mind when she wrote this was Shakespeare. For masterpieces are not single and solitary births. They are the outcome of many years of thinking in common, of thinking by the body of the people, so that the experience of the mass is behind the single voice. And I think that's a really good thing to keep in mind. It's only because of the enormous effort that our society has invested that it's possible for us to do the work we do. So we live in an extraordinary age of astronomical discovery. And for many of us in the audience, we've seen whole fields of astronomy develop from infancy to maturity in our own lifetimes. And I've got a couple of examples of that here. So, for example, radio astronomy, really, after Carl Jansky's seminal observations that Fred mentioned, didn't really get going till after the Second World War. And on the top here, you see the image of Cygnus A, the closest really powerful active galaxy that was made in the early 50s by Jennison Dasgupta. And then you see below it a VLA image by Perley, Dreyer, et al. In the early 80s. And you can just see the level of sophistication that was achieved in, about 25 years. It's truly remarkable. There's no doubt about it that radio astronomy is now really a mature science. Similarly, if you think of infrared astronomy, the top plot there shows the first scan through the galactic center with an infrared single pixel detector by Gary Neugebauer, and he was a graduate student at the time at Caltech. That was back in 1967. And then again, about 20 years, or 1967, 40 years later in this case, you see the two-mass image of the galactic center, made with a 65,000 pixel array. Again, infrared astronomy has gone from not existing to maturity in many of our lifetimes. Similarly, X-ray astronomy. The top plot there shows a very early scan across the galaxy by Gursky, Gorenstein, Kellogg, and Giacconi. Giacconi, of course, won the Nobel Prize in physics a few years ago for this. He was a pioneer in this field. And this is just showing the number of detections that they have from different spots in the sky. They could just detect with their single pixel these things as peaks. And then below you see on the left a beautiful X-ray Chandra map by Jeff Hester and his collaborations. That's of the Crab Nebula. And on the right, a Chandra image of Cassiopeia A in X-rays, Chandra. These were two of the objects that had been seen in the first plot there. Gamma ray astronomy, I'll be talking about that a little bit today, but it's got through its infancy, but I would say it's now in its maybe it's a teenager at this stage, okay? So the interesting thing, of course, is it's not only in the observational side that we've seen amazing advances. As Fred mentions, this has happened in cosmology as well. So when I was a graduate student, the Hubble constant was known only to within a factor of 3, and the deceleration parameter within about a factor of 20. Okay? And now we have a standard cosmological model, the lambda CDM model, and we know the values of half a dozen key cosmological parameters to exquisite precision. This is the WMAP sky of the fluctuations in the microwave background radiation. You see here in this column, WMAP only determinations of certain cosmological parameters, and on this column is basically putting together everything that you can. But, Fred mentioned the age of the universe, 13.7 billion years, 13.69 plus or minus 0.13 gigayears. It's extraordinary to think that we can have that sort of precision, and the precision of the determination of the Hubble constant, the density parameter, the amount of matter in baryonic matter and in dark matter and dark energy, exquisitely well determined. So we live in an era of precision cosmology. And I guess I would say that we can't claim that cosmology has reached maturity because, as Fred pointed out, since we know that we're only studying 4% of the energy content of the universe, and we really don't know very much about the 23% that's dark matter and the 73% that's dark energy, we can't claim that cosmology is mature. But I think that we've passed beyond infancy, and we're probably at the stage now where we're actually able to walk and perhaps beginning to speak. But at least there's been fantastic progress especially in the last 10 or 15 years. So these are some of the instruments that have done this work. WMAP in the center there, which has actually done the most work, but there's a dozen different instruments here. And the extraordinary thing was that these dozen instruments all had to do an extremely difficult experiment, measuring the fluctuations in the microwave background down to the level of about 1 microkelvin, where we're in an environment of 300 Kelvin for most of these instruments, not the ones in space. But nevertheless, they've managed to get this kind of tremendous precision. And I totally didn't expect that we would have this kind of agreement in the microwave background. And we had agreement in the total intensity and the polarized intensity. We've not been beset by unexplained systematic errors. The advance of cosmology has not been a mire of contradictory results with powerful pundits defending their turf. And prior to, there was a period when that was really what was dominating a lot of cosmology. There are plenty of powerful pundits in cosmology today. There's no absence of powerful egos in cosmology and astrophysics. There are more, I would say, than ever before, and especially because since we've welcomed physicists and particle physicists into our ranks, and practitioners of these disciplines are not particularly renowned for their humility. So there's plenty of powerful people, but nevertheless, progress has been fantastically rapid because there hasn't been disagreement. So we've had a very profound change in our view of the universe, and I thought I'd like to just show you one result from the cosmic background image that Fred mentioned before moving on. This is, I meant to mention another thing here. It's not only, of course, microwave background observations. There's been similar fantastic progress from type 1a supernova, which are standard candles, so you can use them right across the universe to measure the geometry of the universe. And indeed, they provided the first evidence of the dark matter, the fact that the universe is not slowing down but accelerating. And then, so that's a completely different approach. And then the other thing, of course, is the abundances of the light elements, which are all produced in the first 3 minutes after the Big Bang. And these also are remarkably consistent with the lambda CDM cosmology. So you've got this consistency over many different experiments and also many different types of experiments, which is very remarkable. And I wanted to show you this one result from the CBI, which I like very much, because I think of all the CBI results, apart from the first one, which was being the first instrument to see the seeds that gave rise to clusters of galaxies, because they were looking on the right angle of scale. It's a nice picture, a display made by my friend Dick Bond, and you'll notice that as we go through 0 here on the top, which is the flat cosmology, the fit of the blue points to that curve is very good indeed. This is showing that we did indeed manage to nail the phase of the polarization. And this was the best result in polarization EE for about 4 years. It's now been surpassed by quad. And so what it told us was that the peaks in the polarization on the bottom tie up with the valleys in the total intensity on the top, and that's exactly what you expect for acoustic waves. And until you had that, it was, of course, an assumption that you were dealing with acoustic waves. This demonstrates precisely, and I don't have time to explain why we've got that phase shift, but I'd be happy to do so. It's a very, very simple explanation. Okay, so that's a confirmation of acoustic oscillations. But today, I chose to a little bit more than about microwave background. So this is the result of a task force assembled by NASA to try to decide what sort of detectors we should be choosing for microwave background work in the next space mission. And I'm just going to show these results. The top is the EE polarization, which is well determined. I've just shown you some determination of those EE curves. Then we have weak lensing, which even though this is in B-mode polarization, which is the polarization that has a curl component, this has not yet been detected, but we know what level to expect because that part of the polarization signal is introduced by gravitating masses along the line of sight from the microwave background. And we've got a pretty good understanding of how much matter there is along the line of sight to the microwave background. So we can predict pretty confidently the level of that signal. So we know we're going to get that. But what people are really after, what people are really after is the long wavelength, the large angular scale. So we have large angular scales down here, small angular scales up here, and the large angular scale B-mode polarization in the microwave background, if it could be observed, would be a direct demonstration or proof of an epoch of inflation, because those signals would be produced by long wavelength gravitational waves interacting with the microwave background radiation and producing this B-mode polarization with the curl component. The only thing that we know that could produce those long wavelength gravitational waves is an inflationary epoch, about 10 to the minus 35 seconds after the Big Bang. So this is now the holy grail in cosmic background research. Everybody's trying to find the B-mode polarization. The trouble is, it would have to be the most optimistic predictions that there are of the level of the signal in order for us to be able to detect it, even with our most sensitive detectors that we're building today. And there are actually estimates of this. Well, it could be zero, of course, because it may be that inflation didn't happen. But there are actually real estimates that range over 20 orders of magnitude for the level of the signal. So clearly, one is taking quite a big gamble if one is investing a lot of time in trying to detect the signal. But nevertheless, if you found it, it would be very important. Okay. You've also got to deal with the foregrounds, which when you get down to 100th of a microkelvin, which is what you're going to have to be able to measure in order to detect that signal, we will have to remove the galactic foregrounds to pretty high precision in all but one patch of the sky. And even there, we might have to do that. Okay, so that's very difficult to do. And I thought that I would talk about something completely different today. And the reason was simply that I think it illustrates the wonders of astronomy and the advantages of working in astronomy there's an incredible menagerie of exotic objects that enable us to study physics in all sorts of regimes. And what I really like about astronomy and why I finally decided that I'd talk about this and not micro background is simply the richness of the situation, plus the fact that I think we've got 3 instruments that are either online or coming online that are going to have a huge impact in this area. The other reason I wanted to talk about this particular subject was because it's what Arya Koenig calls the M word. Okay. I think magnetism is something that is terribly important in all sorts of astrophysical situations. It's probably also important in cosmology. But we know very little about the effects of magnetism in many situations. But as I will hope to demonstrate today, it's vitally important in black holes, the surroundings of black holes, the central engines that drive active galaxies. Absolutely critically important. And I think there are a number of observations that can be made in the near future with combinations of the VLA, the VLBA, the Fermi Gamma Ray Space Telescope, and ALMA that are absolutely critical. And I think there's going to be, I'm confident that there's going to be 0th order advances in this field over the next decade. Okay. I think we'll be very lucky if we see 0th order advances in CMB over the next decade, because I think we're at a level where it's incredibly difficult to push that extra factor of 10. Okay. So I thought I would also give you another little gem that Arya Koenig presented last week. Fred and I were at Roger Blanford's 60th birthday, and Arya was talking about magnetism, the M word as he calls it, and he came across this manifesto about the magnetic fields, and by André Breton and Philippe Soupault. Le Champ Magnétique was the founding text of the Cyrillus corpus. Its authors proposed to explore an uninterrupted form of language, sensing that thought, unobstructed by reason, in stream of consciousness ends up revealing what really wants to be expressed through a kind of magnetic relationship among the different creative connections of the imagination. So I think we're not going to be studying that kind of magnetic field, but I think it's quite interesting that they set out in this direction. Okay, I want to begin now giving you some of the history of the subject I'm talking about today, and 1915 was a very good year for theoretical cosmology. Einstein, of course, published his general theory of relativity in its current form in that year, and Schwarzschild discovered the Schwarzschild metric, okay, which was a solution for, a single gravitating mass, And of course, a direct consequence of the Schwarzschild metric is the existence of black holes. It basically tells us that if you have a mass of size m, then if you can get all of that inside a very small radius, then there is a radius called the Schwarzschild radius, which is 2 times Newton's constant of gravity times m over c squared, and even light cannot escape from within that radius. Okay? So that was absolutely critical. Okay, now there were also, around about the same time, very interesting things going on in observational astronomy and cosmology, and I just chose 1917 as a particularly good year. And for one thing, in 1917, the expansion of the universe was discovered by Vesto Slipher, when he found that 12 out of 15 spiral nebulae spread across the entire celestial sphere were receding from us. Okay? And it was also a good year for another study by Curtis, who discovered this jet in M87. And so this really is the birth of the study of active galaxies and supermassive black holes. I think that's the first observation that directly demonstrated the existence of black holes, but we didn't know it at the time. It took another 35 years until the identification of Cygnus A in 1952. Now, the next important theoretical breakthrough relevant today came in 1964 when Kerr discovered the solution, the metric for a rotating black hole. And so this is the Kerr metric for the rotating black hole, and particularly important for our discussion today is this cross term there. There's a dt by d phi term there. That cross term causes what's called the dragging of inertial frames. It causes space-time to be dragged around by the black hole, okay? And that leads to many of the phenomena, we believe, that we'll be discussing today. So I'm sort of switching back and forth deliberately between, observation, instrumentation, and theory here. So I'm now going to turn back to the early days of VLBI. And of course, right at the start, I should emphasize the incredible role that Barry Clark played in this field and Ken Kellerman. And when Fred and I arrived at Caltech in late 1974, there was already a fantastic development going on in VLBI. And I had the good fortune that the first time I actually went into the library, I picked up the latest issue of the Astrophysical Journal, the October 1974 issue, and I've got ahead of myself because I'm going to tell you a little bit about closure phase. Hold on, am I sure? Yeah, okay. Sorry about that. Okay. Okay, I thought there was a paper. It might come up here, but I'm going to tell you about the paper I read about in 1974 first. I think it might come up later. Sorry about that. But anyway, this paper in 1974 was by Alan Rogers and his collaborators at MIT. And it was the first time I had read about closure phase. Okay, I think it's coming up now, so I'm going to tell you a bit about closure phase now. So, having had the benefit of working in a lab for 6 years where they were doing aperture synthesis, we often used to discuss the relative importance of course, the amplitude and the phase of the Fourier transform. You had to measure both of those, measure the complex Fourier visibility function, Fourier transform that to get the image of the source. And I particularly had a lot of interesting discussions about this with Tony Hirsch, and he used to say things to me like, well, it's odd, though, but it seems as if the phase is particularly important. I mean, we realize both are important, but the phase is particularly important because that tends to tell you about asymmetries in the object, and that's very important for images. And this result actually came out a few years later, but it beautifully illustrates what Tony Hirsch was telling me about. This is a nice simulation done by Oppenheim and Lim, which they published in 1981. So they took an image of an alarm clock and an image of Walter Cronkite. And they combined, on the left-hand side, they combined the amplitudes of the alarm clock with the phases of Walter Cronkite, and they ended up with a picture of Walter Cronkite. Okay? And then they combined the amplitudes of Walter Cronkite with the phases of the clock, and ended up with a picture of the clock. And that beautifully illustrated to me the point that Tony Hirsch was trying to make. I mean, if I was to pick on something, I'd say, well, phase is pretty darn important here. So when I arrived in October and I picked up this issue of Astrophysical Journal, okay, this is the paper that I read by Alan Rogers. And as soon as I saw that closure phase, I thought closure phase has got to be something that could really make the difference between doing modeling, which a lot of people were not that convinced about in VLBI, and making real images. So as Fred mentioned, Peter Wilkinson and I started working hard on this, and just let me explain that the closure phase, so here I'm showing an interferometric baseline on the left-hand side, and you can introduce a little bit of a delay due to the atmosphere or something like that, and that produces a shift in the phase. On the right-hand side there, you've got the interference fringes, and you're measuring the amplitude and the phase of those fringes, and that has produced a shift in the phase. And the beautiful thing that Alan Rogers had noticed, he reinvented this actually, it had been invented some years before by Jennison at Manchester, but Alan Rogers was unaware of that, is that if you look at a closed loop of baselines, like a triangle of baselines, then you get the identically equal but opposite phase shift on the baselines that connect to the telescope 2 there, the one in the middle. And so when you go around the loop adding those phases up, that phase shift cancels out precisely to very high precision, and what you're left with in the closure phase is only information about the structure of the source. And that's very powerful. And of course that, as Fred said, led us to making hybrid maps in VLBI in 1975. And the first map we made was this one of 3C147. We got this map in 75, and it was a one-sided jet. And a little bit later than that, working with Marshall Cohen and Roger Blanford, we made this map of the jet in the nucleus of NGC 6251, and again it was a one-sided jet, aligned with the brighter of the two jets in NGC 6251. And it turns out, and this is an early image, this actually was published by Tim Pearson around about and et al. Around about 1980, but it shows superluminal motion in 3C273. And that's this phenomenon, I think, that you're mostly all familiar with, which is where you see an object moving at apparently much faster than the speed of light. I mean, the separation here is apparently 62 light years. 3 years later, it's apparently 87 light years. So it looks like it's expanding at about 10 times the speed of light. It was very clear after all of these results that what we were looking at was relativistic effects due to objects that were aligned almost directly along the line of sight. These are one-sided jets. They get beamed towards us. We see the jet that's coming towards us beamed. We see the superluminal motion, which is something that you get directly if you have something coming almost directly towards you at nearly the speed of light. It seems to move sideways at faster than the speed of light. It's a very simple calculation to do that. It's just a result of the Doppler effect. So this is all relativistic beaming and projection effects. And so this led us to suggest that quasars and radio galaxies were not as different as they seemed. And we published a paper pointing out, I think we had 4 galaxies and 5 or 6 quasars, that we thought these were the same objects, but just seen from different angles of the jet to the line of sight. So this was the first major pillar of unification theories. The second major pillar, I'm talking about observational pillars, was the realization that these objects have dusty tori around them, which if you're seeing them sideways on, you don't see the central engine. And so then the optical characteristics of these objects look rather different from what they look like if you're looking down the jet. And this was proven by several people, but Ski Antonucci was one of the key people who looked at the spectra in polarization and found that you've got broad emission lines in polarization in these objects, which is clearly due to the scattering of light from the regions of the central engine into the line of sight by particles that are up above the disk. So I think these are the two major pillars in unification. Now, the reason I've gone to all this trouble of telling you all of this history is that, quite frankly, progress since that time has been rather disappointing. You know, we made huge progress in the 70s and early 80s. And because we were making these observational breakthroughs, since then there's been a lot of beautiful work done, but our picture hasn't changed dramatically, and the questions that we're trying to answer today are the same questions that we're trying to answer in the late 70s, early 80s. But I think that's going to change. So I just included here some of the major theories, and which I'm going to talk about. In particular, Blanford and Znayak, I'll talk about that, and Blanford and Payne. This was 1977, 1982, and I will be talking at some length about these two different models for the gamma ray emission in active galaxies, one by Blanford and Levinson, and the other by Marsha et al. Okay, so I want to talk now about electromagnetic extraction from a rotating black hole, and what Roger Blanford had realized was that that thing of the dragging of inertial frames was terribly important. it's now become much more sophisticated, and I'll be going through some of the development of the history to tell you why. So basically what Roger Blanford realized was, so here you have, because of a rotating black hole, because of that cross term that we saw in the Kerr metric, you have a thing that's called the ergosphere. And inside the ergosphere, as I say, space-time is being dragged around by the black hole. Okay. So there's a static limit, okay, and inside the static limit you can't stand still relative to infinity. You get dragged around. Your inertial frame gets dragged around. And then the horizon of the black hole, defined by the Schwarzschild radius, is set inside of that. And this is a picture that was, this actual simulation is from Mitch Begelman. And what Roger Blanford realized is if you have, say, a magnetic field, a 10 to the 4th Gauss magnetic field maintained by an accretion disk, for example, and then you spin a black hole inside that, what's going to happen is that you're going to, from the spinning of the black hole, you're going to set up a very large voltage, okay, a very large EMF, and that's going to be large enough, actually, by pair production, to produce electrons and positrons, so you'll get a magnetosphere in here. And he then showed theoretically that the magnetic field lines are then going to get dragged around inside this ergosphere, okay, by the rotating black hole. And he also showed that the luminosity that you could get out of such a system was set by these expressions here. And so here you see that the luminosity is 10 to the 45 times, this is connected just with the A is the angular momentum of the black hole, and B4 is the magnetic field in 10 to the 4 Gauss, and M8 is the mass of the black hole in units of 10 to the 8 solar masses. So you can see that for a 10 to the 8 solar mass black hole, you can extract about 10 to the 45 ergs per second, which is what we see in a typical large active galaxy. Also, he showed that you could extract about 10 to the 60, 10 to the 61 ergs by spinning down the black hole in this way. So it was clear that you get the luminosity and the total energy from the Blanford-Znayak process. This is some very nice simulations that were done by Komisarov. On the left-hand side, I'm showing the configuration of the magnetic field, and on the right-hand side, we're showing contours of constant angular velocity. So these are recent simulations done by Tchaikovsky on how these objects work. And so you start off with a field line, and then as the black hole spins and drags the field lines around with it, you get that sort of configuration. And so you get the field eventually being toroidally dominated like that. And so you end up with kind of a hoop of magnetic field lines like that. And that's very important for the formation of jets. And we think that hoop stresses can actually confine the jets at large distances along the jet. The stress is due to the magnetic field. And that's one of the key questions in this field is what is confining these jets as they move out from the central engine. This is another very nice series of simulations by Semenov, and basically, again, showing the same sort of procedure. I've got a couple of movies here from this last simulation by Semenov, and I hope you'll be able to see those. So here you have the spinning black hole in the middle. I don't know, can you see that field line? Okay. So it's at first being, of course, attracted because there's plasma out there that's moving along the field lines. And it gets attracted into the ergosphere and starts rotating. And as it rotates, of course, it starts to wind up the magnetic field into a helical field. It's a very nice simulation of what it's very clever what they've done. That paper, if you haven't read it, it's in Science. It's a very clever paper, how they've done the physics right. And this is just a look at the same sort of thing, but from a bit further out. So Blanford, of course, did this back in 1977, but it took about the next 30 years before we could get simulations that could actually show how this would actually happen. So it's pretty impressive the way it builds up those loops of magnetic field, and you get this beautiful helical magnetic field, that moves out along the jet, and then the Hoops stresses of the magnetic field can confine the jet. Okay, so when you're rotating a magnetic dipole like that, of course, there's a lot of, you can get Poynting flux just from the fact that you're rotating this magnetic dipole. And of course, there's been a lot of discussion about, is Poynting flux real? And in this these next observations, which are optical and X-ray observations of the Crab Nebula from Jeff Hester, you can actually see the Poynting flux moving out. You can see the effects of the Poynting flux both along the jet and going out radially as well. So that's the X-ray image on the left and the optical image on the right. So Crab Nebula, of course, is a pulsar, but it's a rotating magnetic dipole. So if you think of what's happening in active galaxies, you can think of it as, I'm going to do two things now. I'm going to move out radially from the black hole, and then I'm going to move out along the jet. First, I'm going to move out in the plane of the disk. So first of all, you begin with the Blandford's-Nyack process, where the magnetic field lines thread the black hole, and they're anchored to the black hole. Going out from there, you get to where the ergospheric winds, which have been studied by Punsley, Carniti, and Coider et al. Here they're anchored in the ergosphere. And going further out, you get this is the paper that Blandford and Payne wrote in about 1982. And here you get threads that are threading a Keplerian rotating disk, and they're anchored in the Keplerian disk. And each of these three winds can drive a jet. So you can imagine that if you were looking end-on, you could see a very fast jet in the middle being driven by the Blandford's-Nyack process. Outside of that, enveloping the faster jet, you could have a jet that's being driven by fields that are anchored in the ergosphere, and then further out, an even slower jet that's being driven by magnetic field that's anchored in the disk itself. Okay. If you're moving outward along the jet now, going along the length of the jet, then above the Keplerian disk, gas pressure propels material upward. You then get into a situation where you've got rotating magnetic field lines, and of course the plasma is these are force-free, and so the plasma has to move along field lines because they're charged particles. And so now your plasma, each of your charged particles is just like a bead on a string. Okay, and so as the field line whips around, it accelerates the particles along the string, and that's how the plasma gets accelerated normal to the disk. So the magnetic field lines are swept back into a barber pole type of helix, and they're accelerated to very fast speeds, the fast magnetosound speed, b squared over a, square root of b squared over a pi plus the pressure over the density, and then they're collimated by the Hoops stresses, okay, of the magnetic field. The Hoops stresses of the magnetic field cause the channel to narrow, and the jet speed becomes highly relativistic. And the physical scale here is 100 to 1,000 times the Schwarzschild radius. And then the jet proceeds at highly relativistic speeds, and we see shock regions out at the level of 1/10 of a parsec to a parsec in VLBI. And Dave Meyer is writing a book on these relativistic jets, and I appreciate very much the many discussions I've had with him where he's helped me understand what's going on. This is a simulation by a postdoc of his and his postdoc's graduate advisor, Uchida. So I now want to show you a VLBI jet by Matt Lister and the Mojave collaboration that extends over a 13-year period from 1996 to 2009. And so this is an object where there's a component here which is moving out along the jet, and it's moving at a speed that's appears to be significantly greater than the speed of light. Of course, it's moving really at a speed that's probably 99% of the speed of light or something like that. I now want to switch gears a little bit and tell you some of the most recent work that's been going on and why I think we're going to be able to crack this problem. So first of all, this is a very nice result published last year by Alan Marsha, in which he's observed an active galaxy, a BL-LAC object, BL-LAC itself actually, and he's been looking at the combination, at the X-ray and gamma ray flux from this object, and he's also looked at visible light and at radio. And one of the great things that he's observed is that the optical polarization angle sometimes rotates very clearly through a large angle smoothly. In this particular case, the polarization angle rotates until it ends up being in the same position angle as a newly ejected component from the core of that object. So here we're beginning to look at what happens, what the magnetic field is doing, and you can also tie together the variability at optical and X-ray and gamma ray wavelengths. But these objects all are peculiar in their own way. The jets have variations in angle to the line of sight, and the components that are coming along the jet have small variations in the angle to the line of sight. And a very small variation can have a very big difference on the apparent brightness of the object because of the relativistic beaming. So in any one object, you have to be very careful about trying to draw general conclusions, because a lot of the time what you're going to be seeing is just the peculiar characteristics of that particular object as components go along, as components shock along the jet or something like that. You have to look at a large number of these objects in order to be able to be really sure of what's going on. And I'll get to that later. So I think a VLBA project where you did a detailed study of the magnetic field and the Faraday rotation in a large sample, maybe 1,000 sources of active galaxies, including different types, Fanroth-Riley type 1, type 2, BL-lax, and flat spectrum radio quasars, to determine the fields in the cores and in the jets, and to look for evidence of toroidal fields and the gas envelope. You want to do you want to do it at multiple frequencies so you can get the Faraday rotation, so you can figure out properties in the envelopes of the jets. And what you would be looking for in a large sample would be the average magnetic field. What one would like to do with the VLBA is a big sample like this and take a couple of hundred of these objects that have the same kind of characteristics in terms of their morphology or type, and then average all of those and look at what is the magnetic field structure in the core and what's the magnetic field structure on the smaller scales. Now, there's been interesting hints so far that, you get switches between perpendicular magnetic fields in the one and parallel in the other. But you want to be absolutely sure that you're finding what is the real generic behavior that's tied to the underlying jet mechanism. That's why this is an excellent project to do with a large sample. I now just switch to the Gamma Ray Space Telescope, and which was launched in June of last year. And the reason that we think this could be very important is because we think it could answer some of these questions. Where do the gamma rays originate? How are the relativistic jets formed and confined? And what is the composition of the jets? Are they electron-positron or electron-proton jets? There's two competing theories here for where the gamma rays come from. The Blanford and Levinson theory, which is, they published this in 1994, and they think that the gamma rays are coming from way down at the base of the jet, very close to the accretion disk, and that what you're seeing is a gamma sphere here with the high energy gamma rays coming from further out than the low energy gamma rays, because inside that, the high energy gamma rays are optically thick to pair production. Okay, so that's the Blanford-Levinson model. On the Blanford-Levinson model, there is some hope of being able to use Fermi GST observations to unlock what's going down right at the base of the jets. Okay. The competing model is the Jorstad and Marshall model, in which the gamma rays are actually coming from the same shocked regions as are producing the radio components that are shocked and seen in VLBA observations. So a long way out along the jet, tenths of a parsec to light months to light years away from the core. No doubt there's a lot of interesting astrophysics you could learn from this model if that's the one that applies, but you're not going to learn about what's going on right down at the base of the jet. Okay. But of course, nature is subtle, and so the chances are that both of these things are going on, and that's one of the reasons why you need to study things in a very systematic way to find out whether or not you can use gamma rays to study the base of these jets. So there's actually a lot of hype in the community at the moment, because there's a lot of evidence that the gamma ray fluctuations are coming from the same knots as are producing the radio fluctuations. The trouble with that is you have to do a lot of correlation before you can be sure that you're actually getting the answer right. What we see is a lot of activity in gamma rays, and we see a lot of activity at radio frequencies. But you need to be sure that the flare that you're tying at gamma rays to the flare that you're seeing at radio is really the same, that those really are physically linked. And for that, you really need to sample a significant length of time. So Fermi-Lat, this is a 3-month gamma ray sky, and they now have a lot more observations than this, of course, but you can see that already they haven't released those. Some of them will be released next week. But basically, they've already detected 106 at this time active galactic nuclei with high confidence. The number has gone up way beyond that since that time. We're observing in two campaigns. One is with the 40-meter telescope. I'll tell you a bit more about that. And one is with a number of telescopes in Europe, including the Effelsberg telescope and the Plateau de Boer telescopes. So with the 40-meter, we're monitoring 1,200 of these blazars twice a week, and we're comparing those with the Fermi GST results. And I'll tell you a bit about that comparison in a moment. It's a fairly large group of people, and I particularly want to draw attention to Joey Richards. It's his PhD thesis, and he's done a huge amount of work to make this possible. Most of the results it's been a result of his very hard work. And Vaso Pavlidou, I'll be talking about her analysis of some of these results and showing you some of that analysis. These are some of the results from the MPI group over a range of frequencies going from all the way up to 1 millimeter, and that is very nice work. It's multi-frequency work that we're doing on about 60 objects pretty frequently at a large range of frequencies. These are some of the Owens value curves. We've got about 1,200 of these. This is over a 2-year period, and we're studying those in conjunction with Fermi GST. This is all I'm allowed to show you at the moment of the Fermi GST results. I'm sorry to say, this is basically about, I think it's 3 months of results just after Fermi GST started. The point I want to make, though, is you can see the radio variations here. The Fermi GST is in red, and you can see that there's a lot of action going on in the gamma rays and in the radio. And you can easily imagine that as we extend the baseline from this overlapping baseline of 3 months to, we've already got about 15 months now, and as we go over a number of years, we'll really be able to correlate between the two and find out if there is a real correlation between the gamma ray and the radio, and whether, the gamma rays often precede the radio or follow them or whatever. So I think this is very important, and the statistics has to be done right. You can't just take one object and say this flare coincides in the gamma ray with this flare in the radio, unless it's got a very distinctive signature that enables you to do that. Okay, so how do you actually analyze variability data? We're doing it in this way, which we're assuming that the variations are Gaussian to begin with. Now, that's not a correct assumption, but we're in the process of checking just how much of a difference that makes. And the first indications are it makes very little difference to what I'm going to be telling you. If the variations are Gaussian, then S naught is the average flux of an object. Sigma squared is the RMS fluctuations in that Gaussian distribution. Sj is a single flux measurement, and sigma j is the noise on that flux measurement. Then the likelihood of measuring flux j is given by this expression here, and the likelihood of measuring mean S naught with a variability index of m is just sigma naught of S naught, is given by this expression. The point I'm trying to make here is that we're trying to do an approach where we do a very careful statistical approach to the data so that we can actually get some significances out of our result in the end. So the value of m that maximizes the marginalized likelihood is then our best guess of it, and we obtain the 1 sigma value by integrating and normalizing in the normal way. So if you do that, then you can get, this is a result on one of our objects, and the maximum then is the most likely result, and there you've got our 1 and 2 sigma likelihood levels there. So we're actually getting real statistics out of this, and that's terribly important, because if you look at this, which is the modulation index for sources in our sample as a function of redshift, you can't tell very well what's going on there, but if you do the proper likelihood analysis, then you find that if we break the sources up into sources that are at redshift greater than 1.1, that's a solid group line of contours down here, and redshift less than 1.1, they're separated by more than 3 sigma. There's no doubt there's a statistically significant difference between the variability in the objects at high and low redshift. And in this case, the high redshift objects are varying less than the low redshift objects. And that's very interesting, because there's all sorts of reasons you can think why that should go in that direction or the other direction. For example, one reason why you might expect the high redshift objects to appear to vary less than the low redshift objects is simply because of the time dilation. We have observed the high redshift objects for a shorter time than the low redshift objects. So we haven't sampled such a large time. On the other hand, the high redshift objects are redshifted, so we're actually observing them at higher frequencies. And these objects vary more at higher frequencies. Okay? There's 3 or 4 other effects that come in here and affect them. But the point is that I'm trying to make is that this is a statistically significant result. That was for all the objects, including BL-LAX. This is just for the flat spectrum radio quasars. We get correlations like this one here. This is the 15 gigahertz flux density and versus the Fermi first 11-month results. And that looks like a significant correlation. But is it a significant correlation? This is apparent correlation in the luminosity at radio and the luminosity in gamma rays. You have to be very careful. I think with this radio astronomy audience, it's well known that you've got to beware of Marquis bias if you're going to look at luminosity plots. And flux-flux plots also, of course, have selection effects that can introduce a false correlation. And in addition, you have to be very careful that you don't observe non-synchronous data, because that can either smear out or artificially induce correlations. So what we have done is we've done a Monte Carlo procedure. We use the redshifts to go to luminosity space, and then we calculate the radio and gamma luminosities for each source. We then permutate the luminosities and apply the same redshift to them to construct mock radio flux and gamma ray flux pairs. Okay? We return them to flux space. We reject those objects that are outside our original flux range. And we then actually pick n pairs and we calculate the correlation test statistic. You repeat that many times. So in this way, you can actually end up with the actual significance of the correlation that you're detecting. And that's very important. Our test statistic that we're using is the Pearson product moment correlation coefficient. And here are the results. Okay? So this is the results of comparing the 2 millimeter flux observations with Fermi gamma ray observations. And this is the actual probability, and the data is way out here. It's very, very clear that the correlation we're measuring is highly significant. And as I step through to lower and lower frequencies, you'll see that correlation goes down. Okay? So this is the Owens Valley 15 gigahertz results versus 3-month Fermi data. And we're right over here, and it looks pretty significant. And this is versus the 11-month Fermi data. And we're right up here. The chance probability we now know with great confidence is only 10 to minus 7. So this is actually the first demonstrably statistically significant correlation between radio and gamma ray fluxes. I'm going to repeat that. This is the first demonstrably statistically significant correlation between gamma ray and radio fluxes. There have been lots of claims in the literature, but they haven't been able to do it in a statistically rigorous way. That's very important. So all we've shown now is that the average flux that we're seeing with Fermi GST and the average flux that we're seeing at OVRO at 15 gigahertz is correlated. Of course, much more interesting now is to look at what happens with the time variability. And that's what we're just getting into now. But I've no doubt that within the next year or so, we will answer the question of whether some of these objects, the gamma ray flux precedes the radio flux, and draw a distinction between the Blanford-Levinson model and the Jorstad-Marshall model. So I think the conclusion here is that gamma ray blazars show significant correlations, and the 100 MeV preliminary first LAT catalog fluxes and 15 gigahertz radio preliminary first fluxes, they're very strongly correlated. Okay, I now want to jump to another area which is highly relevant to what we've just been talking about, and talk about very high energy TeV observations from objects such as the MAGIC telescope and the Veritas telescope. And what we find with these telescopes in M87, for example, is that there are very significant fluctuations on a time scale of 1 to 2 days. And I think there can be no doubt about it that those very high energy particles are coming from very close into the central engine. they cannot be coming from outer shock regions that you're looking at the M87 jet. There's been much discussion. Could they be coming from what's called HST-01, although it was observed as a VLA 20 years before the HST. But they can't be coming from there because they're just they're varying on too small a timescale. That knot is much bigger than the light day across. So these are obviously, so I think we're seeing from the TEV observations that there's activity that we can see that's going on right down at the core of the jets in these objects. I now want to then, I've got two more things that I want to talk about, and it'll be very brief, because I wanted to discuss the things that I think that are of critical importance that we can do with the VLA. And I'm myself convinced that we can do critical observations with the VLA. If we can do that, we want to concentrate on magnetic field. There's a beautiful job being done on the VLBA, so beautiful job being done on the VLBA in looking at how these components move and so on, and evolve with time, and that's very important. And the morphology and so on that's being detected is being studied is very important. But something that we need to study and much more systematically with the VLBA is the magnetic fields in these objects. That's a critical thing we should do with the VLBA. The next thing I want to talk about, there's no doubt about it, is transformational science, and this is work that's being really pioneered by, I shouldn't say pioneered because we did the first observations back in 1981, but the people who are really pushing this is Shep Duleman and his colleagues at Haystack, a number of other collaborators around the country. But these are observations of the Sagittarius A black hole in the center of the Milky Way, and we now know that there's actually the more recent results show it's about a 4 million solar mass black hole. This shows orbits of stars around the central black hole. And we now know that it's a 4 million solar mass black hole. Back to closure phase. If you observe the Sagittarius A star at 230 gigahertz with this triangle of baselines, the longest baselines are getting close to the Schwarzschild radius. They're very close to the Schwarzschild radius. Here you see, this is the Arizona Karma data, then JCMT Karma data, and Arizona JCMT data in Hawaii. And you can see that the central, and this is the radio source at the center of the galaxy, Sagittarius A star. You need to go to high frequencies because at high frequencies you're above the frequency at which interstellar scattering is really important. The point is that the actual angular size that we've observed already is down at this level, okay? And if you look at the central black hole, this is a model by R.V. Loeb and his collaborators. Because of the various beaming effects, you get asymmetric structure if it's not exactly face-on. And you can actually then start looking at the structure in the black hole. The Event Horizon Telescope that's been envisaged by people working in this high-frequency millimeter VLBI is quite an ambitious instrument. But the important thing I would say about it is it depends critically on ALMA. We have to have ALMA at 230 gigahertz to do VLBI. It also depends fairly critically on KARMA, because with KARMA you can phase up all the dishes and you can get a pretty big collecting area. And if you've got two largish areas, then you can do closure phases to all the other smaller telescopes. But you need two largish areas, two largish telescopes to do that. I'm not going to talk about that. Let me just jump ahead to the punchline here. These are simulations by R.V. Loeb of the sorts of structures that we would expect, we might well expect to see for the black hole in the galactic center. And this is showing you the closure phases. And there's really beautiful signatures in the closure phases, which, with the sort of sensitivity that you would be able to get with ALMA in this combination, you really would be able to model what's going on. There's no other way that we can get down to the event horizon of a black hole. The galactic center provides the best object for doing that in terms of, its mass and its proximity. And this is really very important because that means that we could test general relativity in the strong field limit, which you can't do any other way. This is absolutely fundamental science, and I think there's no doubt about it that millimeter VLBI will do this, and ALMA can play a critical role in that. I then want to finish with another project that I think is tremendously has tremendous promise, another VLBA project, and this is the Mega Maser cosmology project. And Fred and I have discussed this many times. I think it's a very, very important project because it's absolutely beautiful results, especially when you use the Green Bank telescope as well, so that you've really got tremendous sensitivity. And when you do that, you get absolutely exquisite results. It's beautiful because it uses all the astrometric power of the VLBA. And these are some of the mega masers that have been detected in this object UGC 3789. And the rotation curves you get, especially these ones, I think, which show Keplerian rotation, are absolutely fantastic. And then, of course, you can also measure the position on the sky. And so basically, you can then solve for the mass of the object, and you can also solve for the distance to the object directly. And in this particular case, it's one measurement. And Jim Condon was telling me yesterday, I hope I quote you correctly, Jim, that the H0 that you've derived and you and your collaborators have derived is, I think, 73 plus or minus 10 kilometers per second per megaparsec. I mean, it's phenomenal. That's one measurement. If you have half a dozen of these, then you'll really be, tying down H0 and going directly to the object without having to go up the normal astronomical distance scale. Another thing that I like to mention to people about this approach is that when the first results came out on NGC 4258, and they were compared with the Hubble key project on the Hubble constant measurement, the people who were working on the Hubble key constant had to renormalize the values that they were using for the Cepheid variables, because it wasn't known whether you could translate the Cepheid variables that you measured in the LMC directly to distant galaxies. It turns out you can't just do that. And so this type of experiment directly corrected the Hubble key project. So I think it's a tremendously important thing to continue to do. And fortunately, nature is kind to us, and there are objects that are bright enough to be able to observe at interesting distances. Thank you. Thank you.
So, if you can entertain a few questions.
Sure, be happy to. Yeah.
Any questions?
Yes.
Various models you have that create the radio jets. How would you explain radio quiet? Like the majority of the quasars are radio quiet. So what would be the explanation?
That's a very interesting question. I think we don't yet know really what makes the difference between a radio quiet and a radio loud quasar. There are a number of things that go, of course, into the recipe for creating a radio loud quasar. And it could be that it's connected with the angular momentum, for example, of the central engine, or it could be with something to do with the feeding. But clearly, it's a very interesting question. And one of the things you really would like to do would be to look at differences. The only thing is that we've got this very beautiful way of looking at all sorts of ordered structures in the radio loud quasars, and we don't have quite the same, ability to attack the. In the radio loud quasars, we can look at that, but in the radio quiet quasars, we don't have the same kind of tools. But I think it's a very, very interesting question.
That's sort of a related question about, in your simulation, you showed a seed magnetic field that was increased by the black hole spinning. Is it like a linear relationship, a factor of 10 to the 10 or something? I mean, if you have a seed magnetic field of some amount, is that, how does that work? Is it related?
Actually, I think the real thing that's happening there is that the magnetic field that you see there is actually anchored to the accretion disk. And then it then gets spun up, okay? And you get a lot of tension in the magnetic field lines. I haven't looked at how that magnetic field develops, but once you've got, well, I do know, let me answer your question this way. Of course, you've got the poloidal component of the magnetic field, which is the one that's going along the jet. And as you move out along the jet, that falls, as r squared, distance from the jet. The toroidal component, of course, is probably only falling as r as you move out along the jet. And then at some point, of course, if the magnetic hoop stress is strong enough that it actually can confine the jet and stop it from expanding, then, of course, you're going to have the the toroidal component is going to project along the jet without changing. But basically, I think the bottom line is that the sorts of magnetic fields that you get into the center could explain the levels of magnetic field that we see further out.
Yes.
Yeah, Tony, you mentioned that the ergosphere around a black hole has a tremendous potential drop,
Right.
and therefore produces pairs. Is it also a relatively modified gamma ray source then? And what kind of luminosity might you get out of it?
I think it could be, although I think that's an interesting question. I think the densities are rather small in there, so it'd be interesting to look at that. But that has all been calculated. It's an interesting question. Yeah, but I don't think we'd be able to see those gamma rays from the ergosphere simply because I think there's too much. They're well within the gamma sphere that Blanford and Levinson were thinking about along the jet. So if you're going along the jet, I think there'll be too much particle pair creation, to be able to see that far in along the jet. Whether or not you could see something sideways, I don't know, but I suspect not. But it'd be an interesting thing to look at. Yeah.
Yes.
Question: in your studies of these active galactic nuclei, do you have any, on some of them, do you have any information on how dense the gaseous environment is around these, in these areas? And if so, can you make any early correlation between the density of the gaseous environment and the possible duration period of time during which the jets are actually activated?
Okay, I think it looks as if the densities of the environments are really too low to confine the jets. That looks to be the case. So it's one reason why we think we might need the toroidal magnetic field to confine the jets. But I think it's something that really merits further study, and that's one of the reasons why we would like to study the Faraday rotation, in VLBA observations of these jets to get some sort of feeling for the plasma that could be surrounding the jets. That would be another way of looking at addressing their density.
If the accretion events which feed the accretion disk happen to bring in material with the opposite spin direction, would that significantly affect the mechanism of the amplification and jet creation process?
I think it could, because you need to. It depends on. I think if you're looking at stuff that's caused way in by the Blanford-Znayak process, maybe it wouldn't. But if you're looking at the sort of jet that we could imagine being driven by the Blanford-Payne process, where you're really relying on the magnetic field that's anchored to the Keplerian disk, that if you brought a lot of material in and it would disrupt the rotation of the Keplerian disk, then it would obviously have a big effect. But are you thinking of what might happen further in than that?
I'm actually thinking if the entire disk happened to be an accretion event which made the angular momentum of it coherently opposite to the angular momentum of the Kerr hole.
Yes.
And whether that's been modelled. I mean, in your models it seems as though they were
No, they're all co-rotating. Yes, that's true.
That's not necessarily the case.
Right. Yeah. Well, I think that'd be a very interesting scenario, but I don't know that anybody's modelled it. Yeah.
The model that we saw with the asymmetry of healing, do we have any hope of actually imaging the asymmetries rather than relying on sort of the information from?
So let me just understand which asymmetry are we thinking of here?
Can you image the...
Oh, you're talking about Sagittarius A star?
Yeah.
Will we have enough resolution to model the asymmetry, to image the asymmetry? Absolutely. I mean, the point about it is that we've already got the resolution needed. We're already getting down to about a Schwarzschild radius in Sagittarius A star, and those features that you were seeing, they were further out than a Schwarzschild radius. So yes, I mean that's why you get that interesting structure in the closure phases. It's because you're actually resolving that. And in fact, if I just go back a step. Here, of course, what we're doing is resolving Sagittarius A star itself, okay? But at this frequency, you're getting down to close to the Schwarzschild radius. Yes, absolutely. So here you see, so this is time in hours here, and here you're seeing this interesting variation in the closure phase, you know, as this central, as the actual image is changing. I mean, I think it's incredibly rich, and the sensitivity that one would need is not ridiculous. I mean, I think we could do it with ALMA and one or two other telescopes. But you do need the big collecting area of ALMA to get that kind of precision. Yeah.
Yes, Mark.
You chose to pass over the explanation of the offset in phase between the polarized peaks, the peaks in the polarized power spectrum of the CMB and the direct power spectrum.
Yes.
And I wondered whether there was a simple explanation you could give us now.
Yeah, there's a very simple explanation. It turns out that the polarized emission is, if you look at it, it's actually dominated by the velocity of the, okay. And so basically what we have is acoustic oscillations. And so, you know, if you just imagine an acoustic oscillation, or you can imagine it as a sort of, you know, an expanding and contracting sphere, just to make it really simple, then, of course, when the sphere is, when this region is maximally expanded, you've got it. When it's maximally, well, I'll go on. I know you've got it, Mark, but I'll explain for you. So when it's maximally expanded, you're going to get it coolest, of course, because adiabatic process. So it'll look very cool. So it'll be a minimum temperature. When it's maximally compressed, of course, it's going to be the hottest, and so getting a maximum temperature. Now, in the plots that I was showing you, of course, we were looking at the power. We were looking at the square of the temperature. Okay. So basically, those maxima come out as being maxima. Now, in between, of course, so you see those maxima, but halfway between those maxima is when the velocity is the greatest, okay? And so it's when the velocity is greatest, and of course, when the velocity is greatest is when you're going to be going through a minimum in the total intensity squared, okay? Because that differs from the mean by the least amount, okay? And so you're going to see the maximum velocity when you see a minimum in the total intensity squared, and at that time you're going to see a maximum in the polarization because that's tied to the velocity.
Okay, let's thank Professor Readhead.
Thank you very much.
And finally, we'd like to present this plaque to Tony. NRAO Jansky Lecture, 2011.
Thank you very much, Red. Thank you. Thank you very much. Thank you very much. I should take another picture. Thank you. Thank you very much. Ta-da. Okay.
Thank you.
Thank you.
Thank you for coming.
Thank you all very much.
There's reception downstairs.
Reception downstairs.